Hello there, Mr. Sutton here, bringing you the BC Calculus 711 Part 1 homework solutions on direct comparison test. For this problem, we're trying to figure out whether this series converges or not. Now, this is a series that is pretty close to the series 1 over n to the fourth, which we know is going to converge. So let's use comparison to that series. So I'll compare it to 1 over n to the fourth. And this is a p-series with a p-value of 4. Since that's bigger than 1, we can prove very quickly that our benchmark, our comparison series, converges. Now, looking back at how that compares to the original, since it has a larger denominator, is actually slightly smaller than this comparison series. So we can write 0 less than or equal to the original series, 1 over 1 plus n to the fourth, less than or equal to 1 over n to the fourth. And this, by the way, shows that both of these series are positive. So, and this is also going to be true for n greater than or equal to 1. It starts being true at 1. So because we have a series that is smaller than a converging series, we know that our original series also converges by the direct comparison test. On this problem, we want to figure out the convergence for this series. Now, this is pretty close to a geometric series. We have 2 to the n, we have 3 to the n. That's pretty close to the series 2/3 to the n, so I'm going to compare it to that series. Now, that series we know is a geometric series with a common ratio, an absolute value common ratio of 2/3. Since that is less than 1, this comparison series converges by the geometric series test. Now, looking back at the original series, since I'm just adding 1 in the denominator, making the whole fraction smaller, this series is actually going to be a little bit smaller than our comparison series over here. So I'm going to write 0 less than or equal to the original series, less than or equal to my comparison series of 2/3 to the n. And this is going to start being true for really all n values, 0 and greater. But you didn't have to go all the way back to 0. You just have to pick any n value where it starts being true. So since I have a series that's smaller than a converging series, that means my original series converges by the direct comparison test. On this problem, trying to figure out whether this converges or not, we go through our litany of tests. The nth term test, this goes to 0 as n goes to infinity, so that doesn't help. And there isn't really a whole lot else out there that's going to help us. Ratio test is one possibility, but it's going to be kind of annoying with this +2 down here. So instead, I'm going to try comparing this to a series that I know converges. Now, I'm going to pick a series that I know converges because this n factorial grows very fast. So this n is kind of a drop in the ocean compared to the n factorial. So let me pick a series that's kind of close and I know converges, like n over n cubed. I'm just going to make sure my exponents on these n's are far enough apart that this is going to converge, because I know that this series reduces to the series 1 over n squared, and that's a p-series with a p-value of 2, which, since it's greater than 1, I know converges by the p-series test. All right, so let me compare this series and the original series. So the original series, we've got a smaller denominator, or a smaller numerator rather. We're subtracting 3. We have a larger denominator. So overall, that's going to give me a smaller overall fraction than this comparison series. So I'm going to write 0 less than or equal to my original, which is less than or equal to n over n cubed. And what n values does that start being true at? Well, for any n value of 3 or smaller, I'm going to end up with a 0 or a negative number even in the numerator, which I'm going to try to avoid because that's just kind of weird to deal with. So let me start at n equals 4. At 4, this is 1 over 26, which is definitely going to be smaller than, this would be 4 over 64, 1/16. So 1 over 26 versus 1 over 16. And if I go to 5 factorial, if I go to n equals 5, this factorial just keeps making this term smaller and smaller than this cubic term down here. So this is going to be true for n greater than or equal to 4. Since I have a series that is smaller than a converging series, I can say my original converges by the direct comparison test. On this problem, we want to know all values of p for which the series n over n to the p plus 1 converges. So this one is pretty similar to the series n over n to the p without the plus 1. So we're going to start by comparing it to that series. Now that series, if we reduce it, this is really 1 over n to the p minus 1 if we subtract those exponents. And this is a p series with a p-value of p minus 1. So this is going to converge if whatever this exponent is greater than 1, which means the p-value here needs to be greater than 2. Now, just to rigorously prove this, if it weren't a multiple choice question, going back here and using our direct comparison test, this series of 1 over n to the p minus 1, or n over n to the p, either of those, this is actually going to be a series that's greater than this series up here. The original series, you're just adding 1, making the denominator bigger. So that original series is smaller than our comparison. So I can write 0 less than or equal to n over n to the p plus 1 less than or equal to n over n to the p. Now, because I've got this series that is smaller than a series that will converge if p is greater than 2, the original series will also converge, and this is, by the way, true for all n values 1 or greater. The original series will converge for any p-value greater than 2 by direct comparison. So that's going to end up being answer choice E. On this problem, we're trying to figure out whether this series converges or not. Now, one way you could do this is comparing this to the series 1 over radical n and using the direct comparison test. However, that's actually taking the long way around. Because we're just having this 3 in the numerator, we can actually take this outside the series, write this as 3 times the series 1 over radical n. Now this series in here we know is a p series with a p-value of 1/2, which, since that's less than or equal to 1, we know that's going to diverge by the p series test. So because we've shown that this series in here diverges, multiplying that by a 3 is not going to change anything, so we've actually finished the problem. On this one, we're trying to figure out if this converges absolutely, conditionally, or not at all. With these problems, we always consider the absolute version first, because if it converges absolutely, then we don't need to figure out any of these other ones. So I'm just going to consider the series 1 plus n over n squared. And this is pretty similar to the series n over n squared, so I'm actually going to compare it to that series. Now that series is equivalent to just 1 over n if I reduce it a little bit. And this is significant because 1 over n, we know that's the harmonic series, which diverges. So now if I compare the original with this series here, the original has a larger numerator, and that's the only change. So the original is actually slightly bigger than my comparison series. So I can write 0 less than or equal to n over n squared, or 1 over n, either way, which is less than or equal to 1 plus n over n squared. And that's going to be true for all n values 1 or greater. Now, since I've shown that I have a series here that is larger than something that diverges, that means my original, or at least the absolute version value of my original, must also diverge by the direct comparison test. So that means I have to go back to the original with the alternating thrown in and see if I can get the original to converge, at least conditionally. Now, looking at this, I've got a numerator that is growing slower than the denominator. So that means that I have an alternating series whose terms are decreasing in absolute value to 0. This is the original we're looking back at now. So that means the original at least converges by the alternating series test. And it's going to converge conditionally because it only converges with the alternating thrown in. On this problem, we're considering the series of a sub n and b sub n, both positive, and n greater than or equal to 1. They're telling us that the a series converges, so which of the following must be true? So this is one where it's good to know the theory behind your convergence tests. This is really speaking directly to the direct conversion or direct comparison test. So for that one, you have two positive series like we have here, and we're basically comparing them, how big they are compared to each other, and drawing a conclusion based off of that. So for the first two answer choices, they're telling us that we have a converging series because they told us A converges, a converging series that's less than or equal to some B series. Well, if using direct comparison, we have something converging less than or equal to some other series, what does that tell us? Not a whole lot. because if you have something that converges and you have something bigger than that converging thing, well, the bigger thing could also be converging or it could be diverging. We don't know how much bigger it is. So we really don't have enough information to pick choices A or B with a converging series less than or equal to our unknown series. All right, so that narrows it down to C through E. Now for choices C and D, we have B less than or equal to a converging series. So let's take a look at that situation. Now if I have a positive series that is less than or equal to some other positive series that converges, that means my original series must also converge. So we do have enough information to conclude that. That is going to then be answer choice C. For this no calculator free response, they're giving us the Maclaurin series for ln of 1 plus x. It's this thing here. That was nice of them. And they're telling us on our interval of convergence, this converges to ln of 1 plus x. Okay, great. And then we have this f function defined as x times the ln of 1 plus x over 3. So a little bit different than what we started with here. Our first task is to write the first 4 non-zero terms in general term of a Maclaurin series for the f function. So we're going to start with the ln of 1 plus x function they gave us, and we're going to do a couple transformations. First thing we're going to do is we're going to substitute x over 3 for x in this Maclaurin series here. So let me write out just ln of 1 plus x over 3 first, and then I'll worry about this x that they have out in front for the f function. So plugging in x over 3 for all the x's, that starts our series with x over 3. That's a pretty easy substitution. Next, I've got x over 3 squared. So that's going to be x squared in the numerator and 3 squared in the denominator. 2 times 3 is going to give us 18 down there, and that whole fraction is negative, so negative x squared over 18. Next, I'm going to have x cubed over 3 cubed times 3. So that's going to be x cubed over, let's see, 27 times 3 is 81. And I happen to know I'm going to need these terms later on, so that's why I'm simplifying them now. But you could wait to simplify them. You don't have to do that now. Next, I'm going to have, let's see, x to the 4th over 3 to the 4th, which is 81 times 4. And that's negative. So I'm going to call that negative x to the 4th over, let's see, 4 times 81. That's going to be 324. Then finally, over here, this is still going to alternate, still going to have n plus 1 power on negative 1. But now we're going to have x to the n over 3 to the n times n. And I'm not going to bother trying to simplify that because that's about as good as it gets. Okay, next one, we're doing the actual f of x function by just multiplying the whole series that we just wrote by x. So let's do that. First term is going to be x squared over 3 minus x to the 3rd over 18 plus x to the 4th over 81 minus x to the 5th over 324, and all this stuff out here, this is going to be negative 1n plus 1, x to the n plus 1 over n times 3 to the n. For this problem, we're trying to figure out the interval of convergence for the Maclaurin series we just wrote in part A. So here's that f series again, and the most important part of this is that general term. To figure out the interval of convergence, since this is not geometric, and you can see it's not geometric because you have this n down here messing things up, we're going to use the ratio test. So limit as n approaches infinity of absolute value of n plus 1th term over nth term. N plus 1th term, that's going to be x to the n plus 1 plus 1, so x to the n plus 2 over n plus 1 times 3 to the n plus 1. All of that over the nth term, so basically all of this stuff. And I'm going to ditch this negative 1 to the n plus 1 because I've got the absolute value already. So now simplifying the fraction a bit, same change flip. In my numerator, I've got x to the n plus 2 times, this flips up to give us n times 3 to the n upstairs. In the denominator, we've got n plus 1, 3 to the n plus 1, and x to the n plus 1. Reducing my exponential terms, these 3's reduce to give me just a 3 in the denominator. These x's reduce, subtracting the exponents, to give me just 1x in the numerator. Now in the numerator, I also have this n term, so we have n times x up there. In the denominator, still have an n plus 1 and a 3 hanging around. As n approaches infinity, this plus 1 becomes irrelevant, so we really just have nx over 3n, ends can reduce in that situation to give me just x over 3. And now to get my interval of convergence, I can start by setting this less than 1. I can also multiply everything by 3, so I get a little bit of a simpler expression on the left. So I have absolute value of x is less than 3 then. And to get at least an initial interval of convergence, I'll just rewrite this without the absolute value. So negative 3 less than x less than 3. But I'll put a question mark here because I still need to figure out if we're converging at those endpoints. So let's test out the endpoint negative 3. At that endpoint, I've got negative 1 to the n plus 1 times negative 3 to the n plus 1. Well, since they have the same exponent, I can multiply the negative 1 and the negative 3 together to get just plain old 3 to the n plus 1. But we have a 3 to the n downstairs. 3 to the n plus 1 over 3 to the n gives us just a 3 in the numerator, and we still have an n in the denominator. So this is 3 over n. Now, if you're thinking this kind of looks harmonic, you're right. You could use comparison to a harmonic series, or even faster, you could just actually factor this 3 out of the series. And then inside here, we see that we do have the harmonic series, which diverges. So we know we're diverging at this first endpoint of negative 3. Okay, well, let's try out the other endpoint at x equals 3. At that one, we have a negative 1 to the n plus 1. We have a 3 to the n plus 1 over a 3 to the n, which reduces to just 3. So there's the series that we have. We still have an n downstairs. Now this one, you could use the alternating series test, but a little bit faster. You can, again, factor this 3 out of here. And we see now inside, we just have the alternating harmonic series, which immediately we can say converges. Okay, so at this point then, since we're converging on the second but not the first endpoint, we can write our true interval of convergence, which is negative 3 less than x, because we diverged at that first one, and then we have x less than or equal to positive 3. For this last part of this free response problem, they're saying p sub 4 is the fourth degree Taylor polynomial for f about x equals 0. So it's actually a Maclaurin polynomial if we're centered at 0. They're telling us to use the alternating series error bound to find an upper bound on p sub 4 of 2 minus f of 2. So basically, we want the error of this. So let me just rewrite the series from part A again. So here's a little bit more of the series. And now we notice again that this alternates and decreases in absolute value to 0, which tells us that we've met the conditions of the alternating series error bound. The conclusion is that the error is just going to be less than the absolute value of the next term. So that's really our setup for this problem. Since we're using the fourth degree polynomial, that means the next term is going to be this fifth degree term, x to the fifth over 324. So our error is just going to be less than absolute value of this term with 2 plugged in, because we're approximating the error at x equals 2. So I'm going to write error less than the absolute value of 2 to the fifth over 324. Now, since they didn't ask us to show that this was less than a certain value, since we've got constants here, you could actually stop here and be done. However, if you wanted to reduce this, this is really 32 over 324. Now, you might remember that 324 was really 4 times 81. That's how we ended up getting it back in part A. So you could reduce these by 4 to get 8 over 81, and that's as good as it's going to get.